projects. In this video, we are going to explain about the project title Deep Transfer Learning for IoT Attack Detection. Before diving into the execution, let me give you an overview of the project. The project aims to develop a method called Deep Transfer Learning to detect and prevent cyber attacks in IoT networks. Deep transfer learning (DTL) involves using knowledge from one area to improve learning in another area, specifically tailored for IoT environments where interconnected devices are vulnerable to cyber threats. This approach seeks to enhance accuracy and effectiveness in cybersecurity measures within IoT networks. Traditional IoT attack detection methods such as rule-based and signature-based approaches rely on predetermined rules or known patterns to identify cyber threats. However, these approaches are inflexible and struggle to adapt to new or evolving attack techniques. To address these challenges, the author of the paper proposes using multiple algorithms, including MMDNet, that is Multi-Maximum Mean Discrepancy Network, AE Autoencoder, SKLAE, Scikit-learn Autoencoder, SMD-AE, Semi-Supervised Autoencoder, Artificial Neural Network ANN, Support Vector Machine SVM, Decision Tree, K-nearest neighbor KNN, and Navy base to create a robust IoT attack detection system. By combining these diverse algorithms, the system aims to effectively identify and mitigate various cyber threats in IoT environments, addressing evolving attack patterns and enhancing overall cybersecurity. To boost cyber attack detection, we have proposed voting classifier. This classifier merges predictions from multiple base classifiers like bagging classifier with random forest and decision tree classifier, enhancing accuracy and resilience in identifying threats within IoT networks. The project evaluates different algorithms for IoT attack detection using metrics like accuracy, precision, recall, and FN score to gauge their effectiveness in identifying and mitigating cyber threats in IoT environments. The project makes IoT devices and networks safer. It helps companies that make IoT devices create more reliable products. Network managers can better protect their networks from cyber threats. Security experts can develop better ways to defend against attacks. People who use IoT devices can trust that their devices and data are safe. This makes more people want to use IoT technology. To implement this project, we need software and hardware requirements. Hardware requirements of the project are operating system of Windows, processor of Wi-Fi and above, RAM of 8 GB and above, hard disk of 25 GB and above. Software requirements of the project are application is Anaconda, primary language is Python, front-end framework is Flask, back-end framework is Jupyter Notebook, database is SQLite 3, front-end technologies used in the project are HTML, CSS, JavaScript, and Bootstrap 4. Algorithms used, these are the algorithms built in the project. And here, these are the algorithms which are proposed in the base paper, which are MMDNet, Multi-Maximum Mean Discrepancy Network, AE Autoencoder, SKLAE, that is Scikit-learn Autoencoder, SMD-AE, Semi-Supervised Autoencoder, ANN, Artificial Neural Network, SVM, Support Vector Machine, Decision Tree, KNN, K-nearest neighbor, and Navy base. And this is the algorithm which we have proposed to further improve the performance. We have built all these algorithms to compare the performance with different evaluation metrics like accuracy, precision, recall, and FN score. And the voting classifier outperformed the other algorithms, and that is the reason we have deployed it in the front end. Let me explain you what voting classifier is. A voting classifier is a machine learning model that combines the predictions of multiple base classifiers to make a final prediction. It operates by aggregating the predictions of individual classifiers using a voting scheme where the most common prediction among the base classifier is chosen as the final output. In the project, the voting classifier is utilized to further enhance the performance of IoT attack detection. Specifically, it combines the predictions of two base classifiers, random forest and decision tree. Random forest and decision tree are individual classifiers trained on the dataset, each making independent predictions. The bargain classifier acts as a meta classifier, aggregating the predictions of random forest and decision tree using a voting scheme. By combining the predictions of random forest and decision tree, the voting classifier aims to improve accuracy and robustness in identifying cyber threats within IoT networks. Now, let us execute the project. To execute this project, first we need to open the code folder, which contains the project source code files. So here, this is the dataset folder. In this project, we have utilized IoT 23 dataset. Let us open this file. So here, these are the different parameters. And this is the target variable. So here we are having two labels, 0 and 1. So here 0 means there is no attack detected and 1 means there is an attack detected. And here this is the attack column in which we are having the different attacks. So based on these parameters, we will detect whether attack is detected or not. So these parameters are features or attributes typically found in network traffic data and are commonly used in network intrusion detection system or cybersecurity applications. So these parameters provide valuable information about network traffic, which is essential for network monitoring, analysis, and intrusion detection purposes. Now let us close this. This is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. This is the templates folder. This folder contains all the HTML pages used in the project. It includes files like index.html, about.html, and more, which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. This is model file which contains algorithm information which will be loaded into the project code during runtime. This is notebook.ipynb file. This is a Jupyter notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. This is signup.db file. This file is the database file used to store user information. First, we need to copy the path of the code folder from the address bar of the file explorer. Here, I'm copying the path. Now open the Anaconda prompt. Use the cd command followed by a space and paste the copied path and hit enter. This command is used to change the current directory to the code folder's path. Compile the app.py file using the command python space app.py. So here I'm typing python space app.py and hit enter. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address localhost, which is this, and port, which is this. Now copy this local link provided by the Flask framework. I'm copying the link and paste this copied link into any web browser. I usually prefer Google Chrome and hit enter. The homepage of the project is displayed in the browser. This is the front end built using Flask framework. If we are a new user, we need to register first. So click on sign up button here. So here we need to enter all these details to register. But I have already registered. So click on click here. So here we need to enter the username and the password which we have registered and then click on login. We have logged in successfully and we are redirected to the prediction page. So here we need to enter all these parameters to predict whether attack is detected or not. Before entering the parameters, let us understand the parameters. So the first one is L4 SRC port. This indicates the source port number of the network traffic packet at the transport layer. Layer 4 of the OSI model. It specifies the port number used by the sending device. L4 DST port. Similar to L4 SRC port, this parameter denotes the destination port number of the network traffic packet at the transport layer. It specifies the port number used by the receiving device. Protocol. This specifies the network protocol used, such as TCP, Transmission Control Protocol, UDP, User Datagram Protocol, or ICMP, Internet Control Message Protocol. L7 Proto. This represents the application layer, layer 7 protocol, such as HTTP, FTP, or DNS. In bytes, this indicates the number of bytes received by the device for the corresponding network flow. Out bytes, this denotes the number of bytes sent by the device for the corresponding network flow. In packets, this represents the number of packets received by the device for the corresponding network flow. Out packets, this denotes the number of packets sent by the device for the corresponding network flow. TCP flags. For TCP traffic, this parameter represents various flags set in the TCP header, such as SYN, ACK, FIN, etc. Flow duration milliseconds. This indicates the duration of the network flow in milliseconds. Now let us enter the parameters from the sample test cases. So here in the code folder, these are the sample test cases. So we will enter these values to predict whether attack is detected or not. So from here, I'm entering the values. So here L4 SRC port is 42050. L4 DST port is 80. Protocol is 6. L7 proto is 7. In bytes is 640. Out bytes is 12815. In packets is 6. Out packets is 12. TCP flags is 27. Flow duration milliseconds is 1558. So here I have entered all the parameters from the sample test cases. Now click on predict here. So here we can see the result. There is an attack detected. Attack type is either DOS, injection, or others. So here we can see based on the parameters, attack is detected and the attack type can be either DOS or injection or others. Now let us enter another set of parameters. Click on prediction link here. So here I'm entering another set of parameters from the test cases. So L4 SRC port is 55525. L4 DST port is 15600. Protocol is 17. L7 proto is 0. In bytes is 63. Out bytes is 0. In packets is 1. Out packets is 0. TCP flags is also 0. Flow duration milliseconds is also 0. Now click on predict button here. So here we can see the result. There is no attack detected. It is normal. So based on the parameters, there is no attack detected and it is normal. Now let us enter on the set of parameters. Click on prediction link here. So let us enter it from the test cases itself. So let us enter these values. L4 SRC port is 35244. L4 DST port is 80. Protocol is 6. L7 proto is 7.718. 7.178. In bytes is 865. Out bytes is 12815. In packets is 6. Out packets is 12. TCP flags is 27. Flow duration milliseconds is 1554. So here we can see the result, that is 1. It means attack is detected. Now let us check here. Click on predict button. So here we can see the result. There is an attack detected and attack type is either DOS, injection or others. Let us enter on the set of parameters. Click on prediction link here. Again, from the sample test cases, let us enter this set of parameters. So here L4 SRC port is 123. L4 DST port is also 123. Protocol is 17. L7 proto is 9. In bytes is 76. Out bytes is also 76. In packets is 1. Out packets is 1. TCP flags is 0. Flow duration milliseconds is 23. So here we can see the result, that is 0. It means there is no attack detected. So here we can see the same, that there is no attack detected and it is normal. So in this way, by entering the parameters, we can predict whether attack is detected or not. And if attack is detected, it can be either DOS, injection or others. Now click on graph link here. So here this is the sample outcome graph which displays the distribution of labels. So here on the x-axis we have the labels, that is 1 and 0, and on y-axis we have the count for the labels. So here 1 represents attack is detected and 0 means attack is not detected. So here we can see that the 1 is having the more count compared to 0. And this is the correlation matrix. And here we have the comparison graphs for the evaluation metrics: accuracy, precision, recall, and FN score. So this is the accuracy comparison graph. Here on the x-axis we have accuracy score and on the y-axis we have algorithm name. Accuracy is a measure of how well a model correctly predicts outcomes. It represents the proportion of correctly classified instances among all instances evaluated. And this is the precision comparison graph. Here on the x-axis we have precision score and on the y-axis we have algorithm name. Precision is a measure of the correctness of positive predictions made by a classifier. And this is the recall comparison graph. Here on the x-axis we have recall score and on the y-axis we have algorithm name. Recall is a measure of the classifier's ability to correctly identify all relevant instances from a dataset. And this is FN comparison graph. Here on the x-axis we have FN score and on the y-axis we have algorithm name. FN score combines precision and recall into a single value. It provides a balance between precision and recall, taking into account both false positives and false negatives. The algorithm which is performing best will be used for prediction. So here in this case, the voting classifier has outperformed the other algorithms, and that is the reason we have deployed it in the front end. Now click on sign out button here.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.